Welcome back to the deep dive. If you've ever looked at a complex crystal structure, say a complicated metal alloy or a ceramic composite, you realize pretty quickly that the real world is three-dimensional chaos.
It really is. And today, our mission is to provide you with the essential shortcut, the toolkit that crystallographers use to take all that 3D complexity and just reduce it to manageable, calculable information.
So we're moving beyond the simple definitions of lattice types.
Exactly. We're focusing on Chapter 7 of Structure of Materials, which is titled Additional Crystallographic Computations. This chapter is really the computational backbone.
The heavy lifting, so to speak.
It is. It provides the methods you need to accurately measure, visualize, and mathematically manipulate crystal orientations in any system, not just the easy cubic ones.
Okay, so let's unpack this journey. We're going to cover four major pillars today. First, the graphical tool, the stereographic projection for mapping 3D onto 2D.
Then the fundamental math, so the vector cross product and the zone equation, which define how planes relate to directions.
Right. And third, what sounds like the universal translator for crystal geometry, the metric tensor, which links direct and reciprocal space.
And finally, coordinate transformations, how we shift our view when the crystal itself changes.
The core challenge, then, is always the same. How do you faithfully represent complex, angular relationships on a flat piece of paper or a computer screen?
Right. If you simply draw a perspective view of a crystal, the angular relationships are completely distorted. We need a method that preserves the crucial information.
So we start with visualization. The very first tool in the crystallographer's arsenal to solve this 3D to 2D problem is the stereographic projection. All right, let's unpack the stereographic projection, or SP. We've all seen crystal drawings, but they are, like you said, misleading. If you draw a cubic crystal in perspective, that perfect 90-degree angle between two faces might look like 75 degrees on the page.
It will, yeah. And we need a way to make sure that 90 degrees stays 90 degrees, at least conceptually.
And the SP does that.
That is precisely the need that the SP fills. It's a really elegant geometric solution. Just imagine placing the crystal right at the center of a large imaginary sphere of radius r.
Okay, so the crystal's in the middle of a bubble.
A bubble, yes.
Yeah.
And any crystal plane we want to track is represented by its normal, the line that's perpendicular to that plane.
So that normal line starts at the center of the sphere, pierces the plane, and then keeps going until it hits the sphere's surface at a single point. Let's call it P.
Exactly. That point P is now the stand-in for the entire plane.
Okay, but P is still on a 3D sphere. We need to get it onto a flat piece of paper.
Right. So now we need to project that point P onto a flat 2D drawing surface, which we call the equatorial plane, the plane that cuts the sphere exactly in half, right through the center.
And how do we do the projection?
To do this, we select a projection pole, and typically that's the North Pole, N.
So the actual projection point on our paper is found by drawing a straight line from P on the surface of the sphere down to the North Pole, N, and wherever that line crosses the equatorial plane, that's our stereographic projection.
That's the mechanism. But there's a problem. If we only use the North Pole, points on the backside, the southern hemisphere, would project miles away from the center.
Making the diagram huge and totally useless.
Completely useless. So we need a convention to keep the visualization tidy and functional.
How do we do that?
Points in the northern hemisphere are projected from the North Pole down onto the equatorial plane. We represent these with small, solid circles, and they always lie inside the main projection circle.
Okay, solid circles for the top half and for the southern hemisphere.
We just use the opposite pole. Points in the southern hemisphere are projected from the South Pole, S, up onto the equatorial plane.
So that ensures they still project close to the center, keeping the map readable.
Exactly. And to tell them apart, these points are represented by open circles. This distinction between solid and open circles is absolutely fundamental. It tells you immediately which way the plane is facing in 3D space.
And what if a point is exactly on the equator?
Then its projection point lies directly on the equatorial circle itself.
The source also mentions we can fix the location of that projected point with coordinates, r, phi, and theta.
Right, and that links the visual map back to computation. R is just the radius of the sphere. Theta is the angle measured down from the North Pole to the point P on the sphere, and phi is the rotational angle in the equatorial plane.
It's basically a spherical coordinate system.
It is.
Yeah.
And it lets us calculate the exact x prime and y prime coordinates on the 2D paper, ensuring total mathematical precision.
Okay, now let's get to the most important property. Why do we go through all this trouble? It all comes down to the fact that the stereographic projection preserves angles between vectors.
This is the defining feature. It's the reason crystallographers use it exclusively. While the SP completely distorts the distance between points, points near the center are compressed, points near the edge are stretched out.
It maintains the true angular relationship.
It maintains the true angular relationship. If two crystal faces are 45 degrees apart in 3D space, their projected points on the SP will still allow you to measure that 45-degree angle accurately. This is crucial for things like verifying symmetry.
And to measure those angles, we don't just pull out a protractor, we use the legendary Wulff net.
The Wulff net is, it's essentially the stereographic projection of a spherical coordinate system itself. You overlay your crystal projection onto it to measure relationships. Standard nets are usually 20 centimeters in diameter and have two sets of interlocking arcs.
Let's visualize those two sets. What are the great circles?
The first set represents the projection of great circles on the sphere. A great circle is any circle that shares the same diameter as the projection sphere itself.
Like the equator.
Exactly like the equator. On the Wulff net, these arcs all intersect at the projection poles. These are critical because they let us measure the shortest angular distance between any two projected points. They're usually drawn every 2 degrees, which allows for extremely precise measurement.
Which ties back to the work of early crystallographers like Carnot, who were physically measuring these angles with goniometers.
Right. They were doing it by hand, or were doing it graphically.
And the second set of arcs?
That second set corresponds to the projection of parallel circles, sometimes called small circles, which are parallel to the equatorial plane. These are really useful for rotational analysis.
This brings us directly to the concept of zones. How does the Wulff net help us visualize a zone?
Okay, imagine a crystal being rotated around a specific axis. We call that the zone axis. Any plane that is perpendicular to that zone axis belongs to that zone.
So as the crystal rotates, the projection point of one of its planes would trace a path on the surface of the sphere.
A circular path, yes. And if we place that zone axis in the equatorial plane of our projection, then the projection of that circular path follows one of those second set of arcs, the parallel circles on the Wulff net.
So the Wulff net isn't just for plotting static points, it lets you visualize and track rotations and relationships between whole families of planes.
Exactly. The Wulff net is the map. Now we need the mathematical tools to plot the precise coordinates for every point on that map. Hashtag 2, 7.2. About zones and zone axes.
To properly define a zone, this sheaf of planes all parallel to a common direction, we need to find that common direction mathematically. And we need a tool that works for any crystal cell, no matter how skewed.
And that tool is the vector cross product. Now, we all learned the determinant trick in high school for the cross product in Cartesian coordinates, x, y, z.
Right. But why does that simple formula fail us the moment we leave the safety of a 90-degree orthogonal system?
Because that standard determinant method assumes that your basis vectors, your A1, A2, A3, are all unit length and mutually perpendicular.
Which is only true for cubic, tetragonal, orthorhombic.
Right. In a monoclinic or triclinic crystal, the basis vectors can be different lengths, and the angles between them are rarely 90 degrees. If you use the standard method on a non-Cartesian system, the resulting vector will not actually be perpendicular to the original two vectors. Hashtag 7.2.1, the vector cross product.
So we need a generalized definition of the cross product that accounts for the skewness of the lattice. Geometrically, the result is still the same, right? A vector, r, that's perpendicular to the two original vectors, p and q.
Correct. The conceptual geometry holds. The magnitude is still what you expect. But the computational expression has to change when the basis vectors are non-orthogonal. And this is where the source introduces the permutation symbol, epsilon ijk.
This symbol looks incredibly abstract. It's defined relative to the volume of the unit cell V. Why is volume the key here?
Because the volume, V, is the one truly invariant property of the unit cell, no matter how skewed the angles get. It ties the geometry together. The permutation symbol used this volume to correctly calculate the components.
So if the indices I, j, k are an even permutation of 1, 2, 3, like 123 or 231, the symbol is plus V.
And if they form an odd permutation like 132 or 321, it's itemi V. And if any indices repeat, it's just 0.
That seems like a really complex way to define multiplication.
It is, but its power is in its universality. By using this symbol, the cross product can be written in a general form that holds for any crystal system, giving us true mathematical flexibility.
And this mathematical generalization immediately shows us the link between direct and reciprocal space.
It does. Remember, the resulting vector, r, is perpendicular to the plane defined by p and q. And by definition, any vector that is normal to a plane is a vector in reciprocal space.
So when we use this generalized cross product on two direct space vectors, the result isn't another direct space vector, it's inherently a reciprocal space vector. The cross product is the computational gateway between the two spaces.
Exactly. And this allows us to finally tackle the zone axis problem. The zone axis, UW, is the direction common to two crystal planes, say H1K1L1 and H2K2L2.
And we can find that direction because it must be parallel to the cross product of the two plane normals.
Which are reciprocal vectors. And the source material provides this brilliant determinant shorthand to compute the zone axis directly from the Miller indices of the two planes. Let's try to conceptualize this calculation for the planes 111 and 120.
Okay, so we set up the indices in two rows and repeat the first two for clarity.
1, 1, 1, 1, 1.
1, 2, 0, 1, 2.
Right. Now, to find the U component, you look at the determinant of the K and L columns. So K1L2 minus K2L1.
That's 1 times 0 minus 2 times 1, which is negative 2.
Perfect. To find the V component, you look at the determinant of the L and H columns.
So that would be 1 times 1 minus 0 times 1, which is just 1.
And finally, for the W component, the determinant of the H and K columns.
Okay, 1 times 2 minus 1 times 1, which is also 1.
So the resulting zone axis, the direction common to both the 111 and 120 planes, is negative 2, 1, 1.
It's a beautifully efficient tool. We don't need to physically plot anything. We can find their common axis just through computation.
And just to close the loop on the geometric rigor, the source confirms that the vector triple product, which involves this cross product, correctly calculates the volume of the unit cell. So our generalized definition is mathematically consistent with the reality of the lattice. Hashtag 7.2.2. About zones and the zone equation.
We've got the math down. Now we can formalize the concept of the zone.
Right. A zone is simply a set of planes, H and KL, that are all parallel to a single common crystallographic direction. And we call that direction the zone axis, UVW.
So if I give you a plane, HKL, and a direction of W, how can you instantly check if that plane belongs to that zone?
You rely on the physical principle we just established, perpendicularity. If the plane is parallel to the direction, then the plane's normal, that's their reciprocal lattice vector, GHKL, must be perpendicular to the zone axis direction, UVW.
And the dot product of two perpendicular vectors is always 0.
Exactly. Which leads us to the universally powerful zone equation. HO plus KDV plus LW equals 0.
That is immense. That single, simple algebraic relationship defines complex 3D geometry.
It is, and the source emphasizes its universality. It is valid for all crystal systems, regardless of whether they are cubic, monoclinic, or triclinic. It's the simplest way to check structural relationships.
So if you want to know all the planes that belong to the 100 zone, you set U1, V0, W0, W0, 0. The equation becomes H times 1 equals 0, so H must be 0.
Right. Any plane with indices, 0, 0, belongs to the 100 zone. It's that simple.
And tying this back to our visualization tool, the stereographic projection, if we place a zone axis at the center of the Wulff net,
then all the planes belonging to that zone must project onto a great circle.
because their normals are perpendicular to the axis.
Right. Their projections must lie 90 degrees away from the projection of the zone axis. If the axis is at the center, the great circle defining the zone is the equatorial circle on the Wulff net. The math and the picture line up perfectly. Hashtag 7.2.3. Reciprocal lattice and zone equation in the hexagonal system.
Okay, we have to pause here because the hexagonal system is always the exception. It's notoriously difficult because it uses that 4-index system.
Yes, the 4-index system is visually intuitive because it respects the hexagonal symmetry, the 320-degree axis plus the c-axis. But mathematically, that third index, I, is dependent on H and K. It's redundant.
Which means our simple zone equation, U plus KV plus LW equals 0, needs special handling.
It does. Initially, you might think to just extend it to 4 terms. But the core problem is deeper. How do we even define the reciprocal lattice vectors in this non-standard system?
The source material has to define new reciprocal basis vectors, A star, B star, C star, specifically for this geometry.
Exactly. And they're defined as these linear combinations of the usual reciprocal vectors. It looks like a complex compromise, but it's necessary to handle the 4-index system correctly.
So we have to go back to first principles, redefine our basis vectors, and then rederive the perpendicularity condition.
We do. And once we substitute these specialized definitions into the condition that the reciprocal vector must be perpendicular to the zone direction, the math surprisingly simplifies down. You end up with a final specialized zone equation just for the hexagonal system.
That whole derivation just underscores that while the underlying principle perpendicularity is universal, the exact mathematical tools you need to express it can change radically with the crystal geometry. Hashtag tag 3. 7.3 relations between direct space and reciprocal space.
So far, we've been talking about vectors in two different forms. Direct space vectors, like a direction ovi, and reciprocal space vectors, like a plane, normal, HKL.
And we need a way to ensure that these two different sets of components, one representing physical location, the other representing periodicity, are actually referring to the exact same physical thing in space.
Right. A physical vector, P, is an invariant. Its existence doesn't depend on how we choose to describe it. But if we express P using direct basis vectors, it has components Pi. If we use reciprocal basis vectors, it has different components, rho I. We need the mathematical bridge between them.
And that bridge is the metric tensor G.
Exactly. You can think of this as the universal DNA profile of the lattice itself. It's the mechanism that encapsulates every piece of geometric information, all the side lengths, A, B, C, and all the angles, alpha, beta, gamma.
So how is this DNA stored?
The metric tensor is a matrix, a 3x3 matrix, built from the dot products of the basis vectors. The source defines two critical versions.
The direct and the reciprocal.
Right. The direct metric tensor, GJK, contains the dot products of the direct basis vectors with each other. This matrix completely defines the geometry of the direct lattice. And the reciprocal metric tensor, GIK, does the same for the reciprocal basis vectors.
And the truly crucial insight here is the relationship between the two.
They are mathematical inverses of each other. The reciprocal metric tensor is the inverse of the direct metric tensor.
And that inverse relationship is the bridge we were looking for.
It is. If you give a computer the 6 basic lattice parameters, it can instantly compute the 3x3 direct metric tensor. By inverting that matrix, it instantly derives the geometry of the reciprocal lattice for any crystal system, even the most oblique triclinic cell.
So if a material scientist is studying a completely novel, non-orthogonal crystal, the metric tensor gives them a clean computational procedure to define its reciprocal structure.
It simplifies the whole process into 3 rigorous steps. 1. Compute the direct metric tensor from your lattice parameters.
2. Invert it to find the reciprocal metric tensor.
And 3. Use the components of that reciprocal tensor to explicitly write the reciprocal basis vectors in terms of the direct basis vectors.
But let's consider the source as example. That tricky monoclinic cell with a 45-degree beta angle.
Right. In that cell, the direct metric tensor will have non-zero off-diagonal terms because of that skewed angle. When you invert this complex matrix, the resulting reciprocal metric tensor immediately tells you the new skewed relationships between the reciprocal basis vectors.
Without this metric tensor formalism, calculating all that would be a nightmare of advanced trigonometry.
It would. The tensor does the heavy lifting, ensuring that the components of any vector, whether UV, duo, or HKL, are accurately translated across spaces. It completes the essential geometric link. #tag find thousands and upper and trend and of transformations.
Okay, now we move to the practical reality of material science. Crystals aren't just studied statically, they're subjected to heat, pressure, stress.
And they undergo phase transformations, meaning their unicell geometry changes. Or, more simply, we might just need to switch our reference frame to simplify our calculations.
Like switching from a large conventional cell to a smaller primitive cell.
Exactly. The ability to change our coordinate system while keeping the physical meaning of the vectors intact is absolutely vital.
The basic transformation starts with a new set of basis vectors being defined as a linear combination of the old basis vectors, governed by a transformation matrix, alpha ij.
Right. This alpha matrix defines the geometric change. But we have to be really careful to distinguish between transforming the geometry and transforming the components.
Because a physical vector, a position in space, is invariant, right? It stays where it is no matter what grid lines we draw over it.
Absolutely. But its components must change to reflect the new basis vectors. And crucially, the new components are related to the old components using the inverse of that alpha matrix.
Wait, so the basis vectors themselves transform using alpha, but the components of a vector transform using the inverse of alpha?
Precisely. If your new basis vectors are twice as large, the components you need to describe the same position vector must be half as large. Hence, the inverse relationship.
That is the foundation of tensor calculus and crystallography.
It is, and it gets even more complicated when we consider reciprocal space. Reciprocal components, like Miller indices, transform differently again. #tag 7.4.1, transformation rules summary, table 7.1.
Okay, the source provides a necessary roadmap in table 7.1. Let's really slow down and stress the distinction between the transformation rules for direct space and reciprocal space.
It's all about index placement. In direct space, things are relatively straightforward. The basis vectors transform with alpha. The direct space vector components transform with the inverse of alpha.
Okay, that makes sense. But now for the more abstract reciprocal quantities, why do they require the inverse transpose?
Because reciprocal components, like the indices HKL, represent periodicity, not distance. They're what we call contravariant components. And when a coordinate system changes, contravariant components transform according to the inverse transpose of the original transformation matrix.
So the rule for transforming Miller indices involves taking the inverse of the transformation matrix and then transposing it.
You must. Failure to do so means the crystal geometry you calculate for the new cell will be fundamentally incorrect.
So the key takeaway for you, the listener, is that you have to rigorously check what you're transforming: basis vectors, direct components, reciprocal components, and apply the correct rule. Alpha, it's inverse, it's transpose, or it's inverse transpose.
That's the whole game right there. Hashtag TagShack 7.4.2, example of a coordinate transformation.
Let's illustrate this with the source's classic example: transforming the conventional face-centered cubic FCC unit cell into its smaller primitive rhombohedral cell.
Right. The FCC cell is a cube with 4 atoms, great for showing symmetry, but the primitive rhombohedral cell has only 1 atom and is much more efficient for computational work.
So we need that transformation matrix, alpha, to define the relationship between the old FCC basis vectors and the new primitive ones.
And we can find that matrix just by visual inspection. The primitive vectors in the FCC system run along the face diagonals. For example, the first new vector is half of the original A1 plus half of the original A2.
That observation defines the transformation matrix, which will be a full of fractions like 1/2.
It will. And once we have that alpha matrix, we can use the transformation rule for the metric tensor to find the new geometry of the rhombohedral cell.
And when you do the math,
The new rhombohedral cell lattice parameters are automatically derived from the old cubic ones. The new side lengths, the new interaxial angle, it all comes out of the math. This confirms that the rhombohedral cell is indeed the primitive equivalent of the FCC cell.
and this framework lets us transform specific vectors too, a direction like 101 in the old cubic frame.
Transforms precisely into -1, -1, 1 in the new rhombohedral frame. And importantly, a plane, like 210 in the cubic frame, transforms according to that inverse transpose rule into the Miller indices 211 in the rhombohedral frame.
The geometry is the same, but the numbers describing it are completely different.
Which illustrates the power and the absolute necessity of these transformation rules. Hashtag TagShack 7.4.3, converting vector components into Cartesian coordinates.
So far, these transformations have been internal to crystallography FCC to rhombohedral, but sometimes we need to exit the crystal system entirely and go back to a standard orthogonal XYZ frame.
For visualization, for simulation, for computer plotting, when you use a computer program, you need Cartesian coordinates.
And we need a general method that works for any skewed crystal lattice.
Right. The source defines a conventional way to set this up. You make your Cartesian E1 axis parallel to the crystal's A1 axis. You put E2 in the A1-A2 plane, and E3 completes the right-handed system. That specific setup is essential for consistency.
And with that frame defined, we can construct the direct structure matrix, alpha.
Which is the explicit recipe for converting any crystal coordinates into Cartesian coordinates. The elements of this matrix are defined rigorously using the lattice parameters and the unit cell volume.
This is the final link in the chain. It allows us to accurately draw the crystal or compute its stereographic projection points.
And because we have 2 spaces, we need a reciprocal equivalent. The reciprocal structure matrix, beta C. This one transforms reciprocal space coordinates into Cartesian coordinates.
And just like the general rule, beta C is defined as the transpose of the inverse of the direct structure matrix.
It is. So if you have a direction over W, you use alpha C. If you have a plane normal, HKL, you use beta C. The system is complete and ready for plotting. Hashtag tag FIFAM 7.5, examples of stereographic projections.
We have the graphical tools, the SP, the Wulff net, and the computational tools, the cross product, the metric tensor, the structure matrices. Now we see them integrated. The goal is to create the maps, the stereographic projections that make the crystal orientation understandable. Hashtag tag 7.5.1, stereographic projection of a cubic crystal.
We start with the cubic system because it provides a baseline of simplicity. Its high symmetry and 90-degree angles make it easy to visualize. We typically center the projection on the 001 direction, placing it at the North Pole, and so at the center of the Wulff net.
Okay, let's break down where the key families of directions would land on this map.
All right. The 100 family has 6 members. 0, 0, 1 is at the center. The 100 and 10 directions lie on the equatorial circle itself, 90 degrees apart, reflecting that perfect right angle.
Then the 110 family, the face diagonals.
12 of those. Directions like 110 and 110 are 90 degrees apart from each other, but they lie 45 degrees away from the nearest 100 direction. And crucially, they all belong to the 0, 0, 1 zone, so their projections must lie on the great circle defined by the equator.
And finally, the 111 family, the body diagonals.
8 of them. And because of the high symmetry, the angle between the 0, 0, 1 direction at the center and any 111 direction is a fixed specific value, 54.74 degrees. So those points are plotted inside the equatorial circle at that calculated angle.
The source material gives a vital warning here that we cannot overstate. The simplicity of this cubic projection, this beautiful symmetry, it's linked to a unique geometric coincidence.
It is. And that coincidence is this. In the cubic system only, the plane normal for the plane HKL is mathematically parallel to the direction HKL.
So if you plot the stereographic projection of directions and then you plot the projection of plane normals,
They look exactly the same. The points overlap perfectly.
that's convenient but really dangerous if you're learning crystallography.
It creates a false sense of security. The text strongly warns that for all other crystal systems, monoclinic, triclinic, all of them, the direct space projection and the reciprocal space projection will be visually and geometrically different. The coordinates you calculate for the direction 110 will not be the same as the coordinates for the plane normal. 110, hashtag 7.5.2, stereographic projection of a monoclinic crystal.
Which brings us to the dramatic payoff of all this computational work. To demonstrate why the metric tensor and structure matrices are necessary, we turn to the monoclinic crystal projection.
We revisit our monoclinic cell example, the one with the 45-degree beta angle. That skewed angle means the plane normals are decoupled from the direction indices. If we try to plot this using the simple cubic rule, we would be completely wrong.
Which means we absolutely must use the structure matrices alpha C and beta C.
Correct. Before we can plot a single point on the Wulff net, we have to follow the procedure. We calculate the direct structure matrix, alpha C. We calculate the reciprocal structure matrix, beta C. Then we use alpha C for directions and beta C for plane normals.
Let's look at the direct space projection first, the directions.
If you take a key direction, say 0, 0, 1, we multiply its components by alpha C. This gives us a specific XYZ coordinate. We then feed those coordinates into the stereographic projection formulas to get the final 2D plot coordinates. The result shows exactly where directions like 101 and 110 land on the Wulff net.
Okay. Now for the dramatic comparison, the reciprocal space projection, the plane normals.
We use the beta C matrix. We calculate the plane normal, 0, 0, 1, by multiplying its components by beta C. And in this specific monoclinic cell, the 0, 0, 1 normal actually does project to the center.
But if we look at a generalized plane, like 111,
The coordinates derived using beta C will be entirely different from the coordinates derived for the direction 111 using alpha C.
and that's the punchline of this entire chapter.
It is. When you compare the visualization of directions and plane normals for the monoclinic crystal, the points do not overlap. The direction vector 111 and the plane normal vector 111 are plotted in two distinct locations on the Wulff net.
This visual separation is the clearest possible evidence of the geometric complexity, and it proves why you need the metric tensor and the structure matrices to account for the distortions and decouplings in non-cubic systems.
The cubic system is the exception, not the rule. The monoclinic projection shows us the true geometric difficulty in most real-world materials. Hashtag tag C6. Historical context and recap.
It's so easy to look at all this determinant notation and matrix algebra and just forget that the underlying geometric truths were established by people using brass instruments and careful manual observation.
Absolutely. The development of the stereographic projection itself is credited to W.H. Miller, who was revising early graphical tools to simplify this exact 3D representation problem.
And we have to acknowledge the experimentalists who provided the ground truth. People like Arnold Karancher, who developed the contact goniometer to physically measure the angle between crystal faces.
Right. His work confirmed the constancy of interfacial angles, which Paul Heinrich Ritter von Graf, the so-called father of German crystallography, championed. The mathematical toolkit we just discussed is simply the abstract method for calculating what they measured manually.
And tying it all back to the computational endgame, figures like Evgraf Stepanovich Fedorov developed crucial physical instruments, like the universal stage for polarizing microscopy.
And to interpret the data from that stage, you need the precise mathematical framework of coordinate transformations and structure matrices. The theory and the experiment evolved together.
Okay, let's consolidate this massive amount of technical detail into 4 essential takeaways you need from this deep dive.
First, the stereographic projection. This is the graphical cornerstone. It solves the 3D to 2D mapping problem by sacrificing true distance to ensure angle preservation. The Wulff net is the grid we use for measurement.
Second, the vector cross product and zone equation. The generalized cross product is the computational core. It's how we find the zone axis, and it's the gateway to reciprocal space. This leads directly to the zone equation, Q plus KV plus LWE0, which universally verifies if a plane belongs to a zone.
Third, the metric tensor. This is the essential geometric bridge. It's the comprehensive DNA of the lattice. Its inverse instantly derives the reciprocal lattice geometry, ensuring we can correctly translate between direct and reciprocal space representations.
And finally, fourth, coordinate transformations. This is the practical necessity. Governed by the matrix alpha, transformations let us shift reference frames or convert crystal indices into absolute Cartesian coordinates using the direct and reciprocal structure matrices. This is required for all advanced computation and plotting.
Essentially, this entire toolkit allows a scientist to take the beautiful, often confusing, intricate geometry of nature and translate it into exact, universally testable mathematics. #outro.
I want you to just step back and appreciate the magnitude of what these computational tools achieve. Every single projected point, every great circle on that Wulff net represents a calculated, precise angle derived through this entire sequence of cross products, metric tensor inversions, and matrix multiplications.
And that precision has a profound physical consequence. Remember the universal stage developed by Fedorov we mentioned? The structure matrices, alpha C and beta C, are the key to unlocking that instrument. A scientist can calculate the exact Cartesian coordinates of a specific plane orientation using beta C. They can then translate that mathematical output into precise rotational adjustments on the universal stage to physically orient the real crystal under the microscope to that exact calculated position.
So that's the direct link. The abstract math of the transformation matrix allows for the physical manipulation and measurement of a tiny crystal in the lab.
That is what truly unlocks material science. It allows us to test theory against reality with incredible precision. We hope this deep dive has provided you with the conceptual clarity you need to master these complex computational tools.
Thank you for joining us for this deep dive into crystallographic computations.
Until next time.